Okay, so now let's talk about variance and standard deviations. Suppose that I have a discrete random variable capital X, and again sample space x1 to xn, and the probability functions PR of something. Okay, we know that the expected value of X is the weighted average of all values with respect to their probabilities. Then we can define variance. So the concept is similar to the definition of variance with respect to a set of numbers. Okay, so now again, we want to ask how dispersed this set of data is, how dispersed this random variable is. And obviously that depends again on the distribution, on the probabilities for each value to occur. If basically all those middle values are having high probabilities, then this distribution is not dispersed. But if extreme values have higher probabilities, then this distribution or this random variable is dispersed. So that motivates the definition of variance in this way. So first, notation. In statistics, people like to use sigma square to denote variance, or say VAR of X. And then what's that? It's the expected value of this random variable, X minus V over 2. To the power of 2. So capital X is a random variable. We use the random variable to subtract, we subtract that random variable X by its mean, mu. Okay? Then that's another random variable. And then we square it, that's another random variable. Then we take an expectation of that random variable. Or write it down is that for each possible value xi, find the deviation from mean and square it. And now we weight this particular value according to the possibility for that value to occur. Okay, then that's the definition of variance. You probably recall that when we have a set of numbers, we calculate its variance in a similar formula. Is that we have this one divided by n. Okay, we have this part divided by n. And that's basically saying that each value has the same probability to occur. We give each value the same weight. Then that weight is 1 over n. Okay, but here each value have different possible probabilities to occur. So that's why their weights are different. Now the weight is probability of that particular value. And then the standard deviation of capital X would be the square root of sigma square. Okay, the square root of the variance. We use the notation sigma to denote the variance and the standard deviation of X. So let's see some examples. Again, suppose that we have a dice and the probability functions is that probability of 1 over 6, the probability of X is 1 over 6 for all the possible values. We know that the expected value is 3.5. So now if we want to calculate the variance, it's the following. I'm going to take each value and find the difference between that value and the mu and square it and do a weighted average. So the first value is 1. 1 minus 3.5 is minus 2.5 and I square it. And then the second value is 2. 2 minus 3.5 is negative 1.5 and I square it. And so on and so on and so on. Because each of them has the probability 1 over 6. So the weighted average is just sum them up and divided by 6. The value is around 2.92. Okay, 2.92. And if we want to find the standard deviation, it's 1.71. Okay, so the calculation is just like this. We know that we have another dice which is unfair, and the probabilities for small values to occur is higher. The expected value we know is 3.15. Now let's consider the variance. Again, we can use the formula and take each value 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 to subtract mu from that. For example, for 1, the difference is negative 2.15, and for 2 is negative 1.15. After we square each values, we now need to use the different probabilities to do the weighted average. Okay? And after that, we get 2.63 as the variance of x. Okay? And one thing we may observe is that 2.63 is less than 2.92. So the variance of rolling this unfair dice is less than the variance of rolling a fair dice. We'll probably want to ask why is that? But intuitively, that makes sense. Because for these particular dice, if I ask you to do a prediction, it's easier, right? Because low values have higher probabilities to occur. So if I'm going to guess one number, I probably want to guess 1, 2, or 3 because it's easier for that value to happen. On the other way, for the fair dice, it's really hard to guess because all the values have an equal value to occur. So when one random outcome is easier to predict, then we say its uncertainty is lower and the variance obviously would also be smaller. We may also calculate the standard deviation, turns out to be 1.62. Okay, so consider another example. Now let's talk about an investment decision. Suppose that I have several possible investment targets. Let's say I have green, red, and white. These are 3 assets that I may invest in, and they also have their yearly growth returns in this way. Okay, so for the green investment is that the outcomes, each of them it has probability 1/6, and with probability 1/6, I get 80% back after 1 year. With probability 1/6, I get 90% back after 1 year. So with some probabilities, I'm going to earn 10%, 10%, or 20%, and so on. The red seems to be quite risky. With 1/2 of the probability, I can get 3 times of my investment back after 1 year. But it's also possible that I only get 6% back. And the white one seems to be very stable. So with some probability, I get 5% of loss, but with only 1/6 probability, I get 10% earning. So these obviously are some investments that we want to consider. Then if I ask you which one do you prefer, there is no standard answer because different people have different risk attitudes. Okay? But when we want to do some measurements, expectation and variance may help. So for investments, we may want to calculate their mean and the standard deviation. So we know how to do that. You may want to verify that these numbers are correct. Like for green, we know how to calculate mean, right? It's just the weighted average of this number and these numbers. For standard deviation, we also have the formula. So you may want to verify them by yourself. And then when we are talking about financial investments, the mean basically measures the expected return, and we prefer that value to be as high as possible. So in that case, the red is really a good one. But the standard deviation also measures the risk or the uncertainty, and obviously most people prefers the uncertainty to be small. Or sometimes we prefer risky project, but the condition, the necessary condition is that its expected return must be high. Otherwise, there is no reason to prefer a risky investment. Okay, so we prefer mean to be high, but we also prefer standard deviation to be low. So most projects are like that. They either have high expected return but also high risk, or the other way. Okay, so in that case, we may want to find a way to do some trade-off. And in the past, financial researchers, they say that we have something called volatility adjusted returns, which is this formula, mu minus sigma square over 2. So I take the mean, take the variance, and plug in them into this formula. I'm going to get one single number that can measure the volatility adjusted returns. And if we do so, simple calculations tell us that green has the highest volatility adjusted return, and that's greater than white, and that's greater than red. So that means if I have no other information, if I just want to follow this formula, I'm going to take the green one, because that balance the return and the risk in some way. Okay, so that's some suggestions from researchers. Okay, thank you.